And now we are going to have Louis-Emile Ploix and Marno van der Maas talking about cosmic verification. And Louis-Emile is delivering end-to-end confidence in CHERI cores at Oxford as an Oxford undergraduate and formal verification engineer at low risk. He works on comprehensive proofs for CHERI-enabled RISC-V processes within the Cosmic project. And Marno van der Maas from low risk, he is focused on building confidence through verification. At low risk, his experience on verification and security enables him to contribute to the vision of making open silicon a reality. So thanks for coming. And
thank you for the introduction, Mike. How's everybody feeling this morning? How's cherry blossoms? We could do a little bit louder than that, can't we? How's cherry blossoms? Yeah, that's what I'm talking about. Thank you very much for coming. Just wanted to say, yeah, it's really an honor for us to be here to talk about verification, and this is really what we believe is the next step in getting CHERI into the hands of engineers. So specifically, we're going to talk about the Cosmic project. As Javier mentioned yesterday, we had our big release. The Mocha repository is now open, so you can go to github.com/lowrisk/Mocha and see everything there. But this talk is really about verification. How are we going to get this into actual SOCs? Is it down arrow? How do I do this? There we go. I was apparently standing too far away. So this talk is in two parts. One part is me going to talk about the overall strategy, and then I'm going to hand over to the expert on the formal side, which is Louis-Emile. So the verification, this is the main strategy. So first of all, why should you believe us? Yesterday in Javier's talk, you saw that we have chips here, so we're not newbies at getting open source silicon into actual chips. So that's what we do. You can go to opentitan.org and you can see not just the RTL, the actual design, but also all our verification collateral and open source dashboards. So this is what we do. This is what we're going to deliver as well for Cosmic. And this checklists are kind of boring, but they're very essential, right? Like anybody who's ever taped out a chip, they know that you have to go through design checklists, verification checklists, and this is the particular framework that we use for OpenTitan. And that's what we're gonna use also in Mocha, and essentially just take every single IP block, every single, and the top as well, through all these checklists, and make sure that people taking this design can have the confidence to to use it with confidence. Now, this dashboard, it's a bit comical because we had to send these slides about 2 weeks ago, and a lot of stuff has happened in the last 2 weeks. So if you go to github.com/lowrisk/Mocha, you can have a link to the dashboard, and it'll look a lot more green than this. But this is really important as well, showing to you where we started from, and essentially showing the trend from green to orange to red. Sorry. Hopefully not that way around. If only I have my notes up, it would be the other way around. So this will hopefully be all green. And as Javier mentioned, Cosmic is a 2-year project, right? So we're going all the way until 2028. And so we're making sure that our progress is open, and you see. But one thing that you might notice is that one thing that's not on here is the CVA6-CHERI core. And that's a really important aspect of this SOC. So what's our story there? So before I hand over to the formal side, which is really cool work, I do want to highlight a little bit of work that we're doing, and we're building on top of the work that Capabilities Limited has done here. So test rig is a way to do instruction. It's a cool way to do instruction generation, but also a cool way of doing instruction injection. And it's been shown to be a very good tool to prove. I shouldn't say prove. To show that SAIL and CVA6-CHERI are in alignment. And one of the things that we're adding to this is having a functional coverage and making sure that we're building this into a verification plan. So we have a story on the simulation side, but now I want to hand over to Louis-Emile, talking about the formal side, and we're just really privileged to be able to work with Louis-Emile, very bright, and also with the rest of the team at Oxford. So please do give Louis-Emile your attention.
Hello everyone, and thank you, Marno. So yeah, I'm going to talk about the fully convergent large-scale formal verification that we've been doing with low risk for CHERI CVA6 as a part of the Cosmic project. And what I mean by that is that we're talking about architectural formal. Yes, so we're talking about architectural verification, not just block level verification, which means that we want to prove that every instruction is correct, its entire execution does what we expect it to do with respect to the ISA specification. And we're going to do that by extending this ISA formal work from ARM, the main difference being that we're going to do it to full proofs. In that paper, they get bounded proofs. Which is quite a substantial difference. So why do we want to do this? Well, we've done this before. We did this for IBEX and we did this for CHERI IBEX, which you've heard lots about already. We've learned that, well, we kind of know what we're doing now. We've also learned that if we do it right, we can actually get value surprisingly quickly for formal, which has a reputation for being a bit slow. And also, it's CHERI, right? And CHERI is kind of complicated, and small bugs do affect security quite a bit. And those bugs are kind of, well, the changes you get from CHERI really affect the whole architecture. So how does end-to-end work? We start with the SAIL specification. That's the machine-readable specification for CHERI RISC-V. We compile that to a combinational system Verilog module. That compiler was written here as part of the SAIL group. This specification module, the system Verilog module, takes as input the architectural state in one cycle, before an instruction runs, and an instruction, and tells you what the next state will be. So it's a function of one state to the next with some inputs. And this is really powerful because we can use it to check that the core, an in-order core, is correct. Because at any given point, when an instruction is about to commit, we can look at what we can abstract the current and next state. We can calculate what the next state should be according to that specification, and then we can just check that they are the same, right? Simple. And so this would tell us that provided the register file and, well, instruction bits and all our inputs are correct now, then they would be correct in the next cycle. Right, so it doesn't tell us everything, though. It doesn't tell us that everything is always correct. It especially doesn't tell us that the PC is correct, because we've not proved, in what I've just said, that one instruction starts where the previous one left off. And that's especially important for showing that you've branched to the right place, or the branch prediction is doing the right thing. It doesn't tell you that the instruction bits are correct, because from what I've just told you, we're checking that the instruction we've given does the right thing. So if fetch just returns garbage all the time, we wouldn't notice at the moment. Well, we're interpreting internal state. So these are all issues we'll come back to. There are solutions we have for this, and we did solve this for CHERI IBEX, and we will solve this here too. Okay, so what have we actually done so far? So we've shown just register file correctness so far. We're in early stages. So all CHERI instructions, a good chunk of the RISC-V instructions and branches, we've shown to be correct 100% of the time in their register file updates, which is a really big statement already, especially for the CHERI instructions, right? That means all of the really complicated bit twiddling they have to do is right. It's quite a big deal. The more important thing, though, and what I really want to talk about for the majority of this talk, will be the sort of framework that we've built up to make this happen, which is a sort of large suite of lemmas that we have that enable this kind of proof to work. There's still a bit more to do, as I said, which we will get to, namely CSRs and PC and exceptions and memory and many other things, but we'll get there. So as a measurement of our success, we can talk about bugs. I don't particularly like measuring the success of formal in terms of number of bugs found, because if we didn't find any, we would still be providing value. But nonetheless, it helps to see that we're actually doing something and that we're not just checking nothing. So we have found a nice handful of bugs. Nothing too severe just yet, but who knows, maybe one day. So this is where the talk gets a bit technical. I promise to do my best to keep it understandable. I'm going to talk about how we actually prove something and how we prove it in a way that we as humans can sort of interact with it, because model checking can be a little bit binary in that either it works or it doesn't. And if it doesn't work, it can feel a little bit hopeless, except that's not necessarily the case. So I'm going to talk about k-induction, which is an algorithm which is a way of proving that a property is correct for a hardware system, which is that it's a sort of extension of the induction you might have done in school, where instead of having one before case, you have k, right? So you start from some arbitrary, maybe unreachable state of the core. You just assign free variables to all of the registers of the state. And you simulate k states, in which all of them you assume that the property you want to be true is true, and then you check that it's still true in the next state. And if that's true, and the base case is true, which is that the first k states are all true, then you have a proof, right? And so there's a sense in which k-induction is a backwards-looking algorithm in that the SAT solver is going to suppose, well, what if the last state is a counterexample? Then let me go back k states and see if there's a path there. And what's really powerful about this is you're like, well, okay, clearly not every property is going to satisfy this, right? But you can prune away those potentially unreachable initial states by writing lemmas. And even more powerful is you can figure out what those lemmas should be. You can play a sort of game with the model checker where you look for spurious counterexamples. So you ask, so what would the trace be if I was going to prove with 5 induction? And you take a look at that trace, you figure out what the problem with it, you figure out a lemma which would eliminate that case, and then you get to assume that of all your states. And so you've reduced the search space, essentially. And you only have to do this a finite number of times before you get a proof. In our case, that's about 430 times, but it's finite. Let's get into a little bit of how CVA6 actually works, and then I can tell you what the proof structure we have at the moment is. So the lifetime of an instruction goes like so. Instructions come from fetch. We don't care what happens in or before fetch. Instructions just appear from fetch. Our proofs say nothing about that right now. They get decoded and they get put into the issue buffer. This is a dual issue core, so there are 2 slots there. When it's ready, when the issue block determines that it's ready, the instruction is issued in order into the scoreboard. The scoreboard is essentially just a FIFO. The instructions are pushed and then popped. When it's issued, it begins executing. Its operands are determined and sent to the relevant functional unit, which is what allows out-of-order execution to some extent. And eventually, that functional unit will finish, and it will write back the results via the relevant transaction ID. Meanwhile, the commit pointer is moving across, committing instructions again in order, which is very important, and the results are being sent to the register file. And so that is, of course, where we can insert our verification. We bolt the spec in, we take a look at what the existing state is, we know what the next state is, so we can compare. And so that looks a lot like the diagram we had before. There is technically one small caveat here, which is that 2 instructions can commit in 1 cycle. So you end up with 2 specifications, but that's not too bad. So everything generalizes. So the question then is, how do we prove that equality? Because writing down the properties, I mean, yeah, the model checker is not going to tell you very much. And, well, the first problem you'll run into when you write down that property is that essentially instructions can hang around in the scoreboard for essentially unbounded amounts of time. There's no bound, or at least not an easy-to-prove bound, which means that you can't, for any k, there's always a longer trace for which there is no such proof. So this property won't work for that reason. So how do we prove the equality? Well, we're going to say that once, the key lemma here is that once an instruction goes into the scoreboard, and in every cycle once it's there, the result is correct. Correct, right? What does correct mean? Well, we'll come back to that. But the key thing to note here is that what you can't write is that the result of each functional unit is correct, and then the result doesn't change once it's in the scoreboard. I encourage you to think about why that's an insufficient proof, but you can't prove it with that. So what is correct? Well, so the obvious thing is to say, well, correct is just whatever the specification says it should be, right? So for each scoreboard entry, we will just evaluate the specification and what we think the inputs should be. and then we check that the result that we're holding in the scoreboard now is correct. The problem is that specification instances are really large. 2 is already a huge pain, so having 8 would really be terrible. So we don't want to do that. So instead, we clone the relevant parts of the core itself, the functional units themselves. So in every cycle, what we do is essentially recalculate what the result should be now based on what the inputs would be. We literally just use the same modules, same instances, well, new instances of the same modules, and compare. And that's really neat, because now what we're saying is that in every cycle, the result is still the result of calculating well, whatever operation we want to do on the inputs. So at the end, when you come to actually prove commit, now you have essentially 2 functions of the same inputs, which you can just check are equal. So it becomes a SAT problem. So now, where do we get these inputs from, right? I'm kind of hand-waving here. Well, in order to figure out what the register file inputs will be, you can forward, essentially, or get the results from the register file, which is almost exactly what the existing native code in the core does. So yeah, guess what? We can just clone the relevant part of the core again. Maybe we're going to see a pattern emerge. And yeah, now the other input we need to think about is the instruction bits themselves. So how do we prove that we're providing the correct instruction bits? Well, you do that by cloning the decode and showing that in every cycle the instruction is still decoded correctly. So I hope you agree with me, but a methodology is beginning to emerge, which is that we seem to do a lot of cloning of internal components of the core itself. And yeah, we saw this in IBEX as well, and this has become quite interesting. In IBEX, we were dealing with the memory unit, and we ended up with 3 clones of the LSU. Interesting. The objective is always to flatten time, essentially, right? Model checkers are quite bad in general, but SAT solvers are really good. So if you can turn your problem that is spanning time into a problem that spans only a single cycle, then you have just a SAT problem. So you just want to reduce any problem you have into a comparison of 2 different functions of the same inputs in 1 cycle. And so this is sort of symbolic execution, but backwards. The other thing we need to think about is capabilities. It's the other major part of the proof I've not talked about. You need to constrain what a valid capability can be. For example, tagged capabilities are going to have their reserved bits 0. If you don't have that, then instructions just won't be correct. The CHERI unit assumes that instructions satisfy some properties, and that's one of them. Things like if you have the implied exponent, then the exponent is what the implied exponent would be. Sort of obvious things that, well, some of them are obvious, and then some of them end up being less obvious, and those are the interesting ones, that you have to write down, and without them, you essentially can't get a proof, because again, you have this problem of you could come up with a trace of any finite length, and you could just assume that there's a capability in the register file to start with that doesn't satisfy these constraints, and then it will just hang around forever. So you need this property, and you need that not just for speed, but for to get convergence at all. And how do you prove that? Well, you essentially look at every single capability in the system, and you just check that in every operation that would mutate them, this is still maintained, and so in every cycle, every capability maintains this property. So that's been a little bit detailed, and I hope you followed. At a high level, though, what we've shown is that instructions are hopefully correct with respect to each, well, the execution of each individual instruction is correct. The eventual plan is to show what we call observational equivalence, and this is what we did for CHERI IBEX, and this is what was so powerful, in that for CHERI IBEX, we showed that the infinite sequence of memory operations produced by the specification matches that produced by the core. So they're essentially indistinguishable from one another. And that's a really high, I mean, that's essentially the highest level of guarantee you could ask for, right? And that's what we did for CHERI IBEX, and that's what we plan to do here as well. We haven't yet, but that's the plan. So to conclude, we're in the process of showing that CVA6-CHERI is correct. We've done a lot already. We have plans. We have a really high level of confidence in the parts of the design we have formally verified. And for those that we haven't yet, DV gives us confidence too. So thank you for listening.
Thank you. Any question? Okay, everyone has followed all the formal proofs. Okay. Yes.
Thank you for the talk. You haven't talked about your specification language. What specification language do you use?
Sale. So both RISC-V itself and Sale RISC-V have like authoritative sale specifications, which are machine readable, and there's a really good sort of tooling behind them, which allows you to translate them into System Verilog or SMT or Isabelle or whatever else.
Thanks.
Thank you. So, related question. How much confidence do we have in those specifications? Because it's no
Well,
good proving
technically-
something against an incorrect specification.
Unless I'm mistaken, the RISC-V specification itself is, the sale specification is ratified. So that is the source of truth. Am I right? It's not technically ratified. Okay. Okay, my bad. It's close to ratified.
What I'm
So,
getting at is that in the past,
I guess we can say that our proof is specifically conformance to the sale. So if your sale is wrong, then yeah, I guess our proof is wrong. There's not much we can do about that because the English language one is not really something we can directly prove equivalence to. So yeah.
no, it's just that what we've done in the past, and I'd really love to see again, is proofs about the sale,
Oh,
about
sure.
the security properties of the sale, and then that carries through to your work, which would be
Oh,
brilliant.
sure. Yeah, I think there's been some work on the sale here as well. So yes, there's some security properties that have been proven at the sale. I'm not an expert on what exactly, but there's some stuff.